Electrostatic precipitators, or ESP, are filtration devices that remove fine particulates like dust, smoke from a flowing gas using electrostatic force. It's used in industrial settings to control air pollution by capturing particulates. So it's mainly used in coal-fired power plants because the particulates that come out of burning coal is really, really small and they are very harmful. And they are also charged a lot. So the ESP works very well for this technology. So for ESP, particles are charged and then collected on oppositely charged plates. Look at these two plates over here. Can you see this plate on the left and this plate on the right? These, they have charges and the gas is flowing right in between them. So while the gas is going, the particles will be drawn either to the right or to the left plate based on the charge of the particle itself and leaving the gas itself to come clean from the other side. There are other components of this system. The corona, which is high voltage wire to charge your plates. You have your ground. You have your removal hoppers. That's where the particles settle down. Wires. So the particles are charged, then collected on oppositely charged plates. ESP is similar to gravity settler or centrifugal separator. However, what really works here or dominates is the electrostatic force that drives the particle to the wall. It's effective on much smaller particles than both of them. So it is a two-step process, particle charging and particle collection. Because all what I've described so far is particle charging. If the charge remains the same all the time, what will happen? The particles will keep attaching to the surface until the surface cannot really take any more particles, and then it's ineffective. So we really need to get rid of the particles that are on the surface. So once we stop the flow from these plates, and then we can stop the charge, particles will fall down because there is no attraction anymore to the surface, and then we can collect them into the hopper. So what do we need for this design? We need high voltage electrodes and collection plates. Advantage of this technology, that's very efficient and can handle a very large volume of gases. The disadvantage that it's really expensive. It's very high initial cost. And because it's very complicated system, it requires a lot of maintenance to be done to the system. So the high voltage wires, they are typically in the range of 40,000 volts. And that's really, really high. You need grounded collecting plates, transformer rectifier to generate the high voltage, mechanical or electromagnetic wrappers to remove collected dust from plates. It's used mainly for power plants, the coal-fired, cement plants, steel and iron manufacturing, paper mills, sulfuric acid plants. So this is the main equation that we use for the ESP. Q is equal to 3 pi epsilon over epsilon plus 2 epsilon naught d square E naught, where Q is the charge of the particle, epsilon is the dielectric constant of the particle. This is the dimensionless number, 1 for vacuum, 1.0006 for air, and 4 to 8 for typical solid particles. Epsilon naught is called the permittivity of free space, and it's also a dimensionless constant whose value in the SI system of units is 8.85 times 10 to the power negative 12 coulomb per voltmeter. D is the particle diameter, and E naught is the local field strength. Let's look about the example over here. A 1 micrometer diameter particle of material with dielectric constant of 6 has reached its equilibrium charge in an ESP at a place where the field strength is 300 kilovolt per meter. How many electronic charges has it? So we are looking for Q. So we'll apply this formula. Q is equal to 3 pi epsilon plus 2 epsilon node d square E node. Now we have 3 pi epsilon is 6, which is mentioned here. So it's V6 over 8, epsilon plus 2. Epsilon node, which is a constant, and we know how much is the constant, 8.85 instead of 10 to the power negative 12, times d square, which is 10 to the power negative 6, it's 1 micrometer diameter, square, times 300, and 300 here will be your E node. That's given in the example. So, and if you solve this, you will come up with 300 electrons. So the value computed in this example is typically for a large particle, and the charge is proportional to the diameter square, so that a 1/3 micrometer diameter particle would be expected to have about 33 electronic charges. So you can see that 300 for 1 micrometer, 33 for 1/3 micrometers. Moving forward, the electrostatic force on a particle, EP, is local electric field strength. F is equal to QEP. F is equal to 3 pi epsilon over epsilon plus 2 epsilon node d squared E node EP, which is the same like what we did before. It's just we're adding the EP to the equation. Now VT, which is the terminal drift velocity, is equal to omega is equal to d epsilon node E square epsilon over epsilon plus 2 over mu. So in this example, calculate the drift velocity of the particle in the previous example. So we'll calculate the omega very easily just by know everything, and we'll divide by mu. We'll get that it is equal to 0.033 meter per second or 0.109 feet per second. If you consider the sections between the row of the wires and one plate, you see its collecting area. Q is equal to A is equal to LH, and Q will be H times small h, the average. And again, for two types of calculations, we have the block flow and the mixed flow. In the block flow, the collection will be equal to omega A over Q. And for the mixed flow, it will be 1 minus e to the power negative omega A over Q. So in this example, compute the efficiency diameter relation for an ESP that has particles with dielectric constant of 6, and A over Q equals 2.2 minute per foot. Use mixed flow equation. So we'll use the second one, and eta is equal to 1 minus e to the power negative omega A over Q. So we have everything here given. That will be equal to 2.73. We can do this for different types of particles, different diameters of particles, and we'll come up with the table that's here on the right side of the slide. Next video, we'll be talking about the dividing collection devices.